Cause you on the Central
All right. How are you guys today?
Doing great, man.
I'm very glad to hear that.
Can't complain. I can start answering that. I do, I just be wrong.
All right. At this particular point, we've gone over all the information specifically within chapter 4. So I feel like we've got a good baseline established for Newton's laws and different types of forces. So main objective for the day is to begin chapter 5.
Will chapter 5 be on our test?
It will. And that's why I'm wanting to start it today, so that if it takes us about a week, we'll finish up next, meeting 3 lectures. We'll finish that up on next Wednesday and have a full day on next Friday to get ready for said test. I'm gonna put a calendar up quick to have something to point at when I'm talking about these dates. Today is Friday, September 22nd. My goal again is today to begin talking about chapter 5. It'll be the last chapter before our first test. Test 1 will be on chapters 1 through 5. If we start chapter 5 today, my goal is to be wrapping it up by next Wednesday, the 27th, so we have next Friday, the 29th, to review it before the week of our first test, October 2nd through 6th. Any questions or objections to this general plan? All right. Yes.
Our test on October 2nd.
The test will take place the week of the 7th through the 6th. You'll show up for lab, and then you'll have 3 hours to take a 1-hour test during lab. So there won't be an actual lab activity that week. We're just using lab time so that you don't have to rush in and do an hour test in 50 minutes and then rush back out. So whenever you would attend lab this week, you will show up and take the test instead.
So you take it on the 6th?
Apologies if that hasn't been clear. So I need up a second ago. Someone else have a question?
Yeah. If like your lab day is the same day like that we would have class, are we still having lecture?
There will still be lecture the week of the test. The lecture will be primarily aimed towards helping people prepare for the test.
Okay.
As a reminder, I've said this a few times, but I'll say it again, and we'll spend more time focusing on it in class. For every test, that includes both normal tests and the final, I create a study guide, which is to say the list of concepts you should be familiar with. I point out what things on the formula sheet relate directly to those concepts, and I make a practice test, which is a bunch of questions similar to the test questions, obviously not identical, but written in such a way that if you can comfortably do the practice test, you should do well on the test itself. All that study material, I aim to have it completely ready by Friday the 29th, which is the day I'm planning for us to be able to review everything we've done so far before test week starts. And my goal is lectures during this week will be aimed towards people going over, like if you guys go over that review material, we can look at it together in class on those days as well as the homeworks and the quizzes. I want to stress, the homeworks and the quizzes are also good practice for the upcoming tests. Test 1 will be on chapters 1 through 5, so to help study for that home test, you should also do homeworks and quiz chapters 1 through 5. I want to make that doubly extra clear because right after test week, the following week, midterm scores go out on Friday the 13th. It still feels weird to say out loud. And what this course's midterm score is, it's not just your test grade, it is your current course average. Meaning it'll be your test grade averaged in with your lab score, your homework score, and your quiz score. Now, the homework and quizzes aren't due until the end of the course. So if you haven't been doing them, It's technically fine. I recommend doing them, but I'm not gonna force you. But if you haven't touched them yet, that is technically gonna be a part of your midterm score. Meaning if you haven't touched them yet, the midterm score will be artificially lower than you might expect. So, more reasons to be working on them. And that means that that's another thing that we can work on together in lecture the week of the test. Now, if that week is mainly test review, you don't have to show up if you don't want to, like even more so than usual.
Like, what if my lab's on a Monday and I took the test on Monday?
Yeah, in that case, the lectures that week, like the Wednesday and Friday lecture then, would still be about test review, meaning the most you'd probably get out of it is refresher, maybe time to ask about homework stuff you're still working on. Yeah, showing up, if you do take the test on Monday, lecture on Wednesday and Friday is not strictly speaking required. If you take the test early in the week, you can take those days off if you wanted to.
Just sound disappointed.
I still like it when people show up and ask questions, but if you don't have any questions, then enjoy yourself. Now, you could take the test on Monday, get it over with, and take the rest of the week off. You could also take it later in the week and spend the lectures practicing. I'm leaving it up to you guys, since, again, you can normally attend any lab in the week, and therefore you can also attend any test slot during the week. Some people go out of their way to take it early and get it over with. Some people go out of their way to take it on Friday and get as much study time as they want. I leave it to you.
So we can just show up at the lab we want to take it in?
Yes,
Okay.
whatever lab that you want and that fits into your schedule.
Do you curve the test?
I don't curve it, but there is one, I do give partial points for literally everything. Again, if you write a frowny face, you get at least 1 point. Because that's an answer. It's not a great one, but it's an answer. Furthermore, all my tests have bonus points built in. I don't like doing one bonus question because then if you don't know it, you don't benefit from it. So instead, I just give you more points than you need to get a 100. So not a curve, but there's other ways built in to make sure people have an okay time. Does that address your concern? Okay. Yeah, I graded out of 100, but all the point totals still add up to 105. Each question will tell you how many points it's worth. If there's one like big 25-point question and it feels tricky to you, that's okay. Getting that question perfectly is like the difference between an A and a B. I'm rambling at this point. How you guys feel? Any other questions or concerns for right now? Namely, any questions before we move into Chapter 5 territory? If you've been working on, say, the Chapter 4 homework, any issues about that before I switch gears? Alright. Again, do please ask me questions about anything, anytime, even if it is not relevant to what I am talking about in the moment. Chapter 5 is actually going to be a direct continuation from Chapter 4, but we're going to be adding in a few new principles to continue examining the forces and the laws of motion we've been discussing. We've been talking about force, how forces all interact with each other, and you've been exerting forces with your body for as long as even since before you were born, if I'm being honest. I am sure that you've noticed, even though you are capable of exerting force with your muscles, that doing so for long periods of time can be taxing, right? You could use about 3 newtons of force to lift this remote. And you could keep doing that over and over again. But eventually, even though you are capable of exerting that much force, your arm's gonna get tired, right? The force you exert is connected to, but technically separate from, why that happens. Whenever you exert force, your body has to use energy in order to do that. And in terms of the physics definitions of all those terms, the energy you use up performing a task is called work. The physics definition for the term work is the use and transfer of energy, alternatively thought of as the transformation of energy. And every single time you have ever used force, and I mean any force, that includes your arms, it includes blinking your eyelids, it also includes the things that you don't consciously think about, like your heartbeat. Any one of those forces uses up energy. And the way that we figure out how much energy a given task consumes is you take the force that task required, multiplied by the distance that force is applied. Whenever you push something, your usual goal is to push it a distance, right? And so that means, like, I've been talking about pushing heavy things on moving day for about a week now. Your goal is usually, I have a box here, it needs to get there, so I'm gonna apply 100 newtons of force and slide it like 2 meters, right? Those are the two things that multiply together to tell you physically how much work is performed when you use that, when you do that task, how much energy it takes you to perform that task. And again, this happens every time you use force, even the weird internal forces of your biology, like your heartbeat. So, new variable, that's the W here in this formula, work. Work equals force times displacement. In order to accomplish work in the physics sense, you have to exert a force, and that force has to successfully move something a distance. And so technically, anytime you move your own arms around, you are doing work because your muscles exert force on the mass of your arm, and your arm moves a distance. Again, literally everything you do involves force and therefore does work and therefore drains energy from you. Yes?
What does the P stand for?
That's an excellent question. I keep not tweaking that. That P is supposed to be a parallel, yes, a parallel symbol, actually. So if you look at your formula sheet, I'm going to direct your attention to where this formula is on the pre-written sheet, as soon as I find it.
It's under Hooke's law.
Energy stuff.
Thank you. Right here, the top of the energy stuff bracket, W equals work times displacement. On the formula sheet, it does have the symbol correct. Instead of P, it's written the parallel symbol. So if you're writing this down in your notes, you should use 2 parallel lines instead of the letter P. Because frustratingly, the opposite of parallel is perpendicular, and that starts with the same dang letter. The reason that is there is because, again, physics definition, in order to successfully do work, you have to apply a force, and all forces are vectors. You are always pushing in a direction, right? Push something with 10 newtons of force, and then it has to move in the same parallel axis as that force. In order for, again, in the traditional physics sense, for you to be accomplishing work, for you to be successfully using your energy and getting the task done, the force has to be parallel to the displacement. And so that's why that symbol is there. They have to be in the same axis for this formula to work right. So, if you are pushing a box to the right and it moves to the right, you are the one doing that work, and successfully you are getting a task successfully accomplished. If, on the contrary, you are pushing something and it doesn't move, you may be using up energy, but it's not actually moving parallel to the force, and therefore you're not accomplishing anything. You're just kind of burning energy pointlessly. So that would be like me just pushing against the wall, trying to knock it over, but that's not gonna work, is it? I'm exerting force, I'm using up the energy in my muscles, but I'm not actually moving the wall and not getting anything done. Delta X would be 0 in that case, and I get nothing accomplished. No matter how much force I use, if the wall doesn't move, work accomplished equals 0. Likewise, if I'm pushing the wall sideways, and separately a crane comes along and lifts the wall up, I'm also still not accomplishing anything if the wall moves up when I push it sideways. The crane's accomplishing something, right? In that case, I'm trying to push sideways, the crane is pulling up, and the thing actually displaces up. The crane's force is parallel to that displacement. The crane is doing something successfully. My force is not parallel to that displacement. I accomplish nothing. The crane is lifting the wall. All I'm doing is tiring myself out, probably being an inconvenience to the crane operator. So that is why that symbol is there. The force has to be parallel to the displacement for you to actually be accomplishing something. I forget who asked. Did I answer the question? Okay. We will come back to that. It'll be an important part of the math. But I'm glad you asked. While we're here, work is a new variable, so I want to make sure to define everything you need to know about it first. Work, variable uppercase W. So if you see uppercase W in a formula, it is referring to work. And in physics, again, we define work as the energy used up in a task, the energy transferred between objects while doing it, or the energy transformed as a result of the process. Because whenever you do work, you are really giving up some of your own energy. When you push something, you are putting energy into the box in order for the box to be able to move. And that means you don't have that energy anymore, right? When you push something around, you are physically tired afterwards because you have less energy in your body. So again, work, when you do work, you are giving up energy, giving it to something else, and possibly putting that energy into a different form along the way. Because work is a measure of energy used, the unit for work is the same as the metric unit for energy, and that is joules. There's actually, I guess, 2 standardized units for energy, the other being calories, which you may prefer depending on which floor of this building you hang out on the most, or the adjacent building. No, it's that way. Joules and calories measure the same thing. The difference between them is basically the same as between meters and feet. Which you prefer just kind of depends on your discipline of choice. In this class, we're going to use joules because all of our formulas are designed to accept and then give us joules back out. But there is a direct conversion between the two. 1 joule is about 1/4 of a heat calorie. That does also mean that the calories on the food you eat directly translates to the energy you get from the food, because calories is, again, a unit of energy like joules is. So, new variable is work, measured in joules, spelled like this. It's a French name, not gemstones. And the unit is uppercase J. So the variable's W, unit's uppercase J. I feel like I'm repeating myself over and over again. How do you guys feel so far? Okay. So, we've defined work. That said, the definition of work uses the word energy multiple times, and I haven't formally defined energy yet. So let's do that. Energy, scientifically speaking, academically speaking, is weird. And we still don't really know exactly what it is, because we can't see it. Energy is this invisible, intangible thing that matter can possess. And you can't detect it directly. Anytime you think you can detect energy directly, you're actually detecting it indirectly. You cannot detect the energy itself. You can only detect what the energy does or what the object that has the energy is doing with it. Off the top of your head, when you think about energy, possibly about perceiving energy, what sorts of things do you think of? Heat, that's a good example. I'm going to put that over here. Thermal energy is a form of energy.
Electricity.
Very good. Any other thoughts?
Kinetic energy.
Very good.
Potential energy.
Static electricity.
Yeah.
That's still a type of electricity, but you are correct. All right, light, very good. This is a good list. Now, all of these do involve energy, but all of them, technically speaking, light's kind of an outlier there, but I'll get to that in a minute. None of these things themselves are directly energy. You do perceive these things around you in some way, but they themselves are not the energy themselves. Matter possesses energy. Matter does stuff with energy. And most of these things are examples of things that can happen when matter possesses energy. So go down the list. When matter possesses thermal energy, its temperature goes up and its particles start moving around more, right? The motion of the particles happens because the object has energy. And the only way that you perceive that energy is if you touch something that has the energy, right? You cannot look at an object and directly know what temperature it is. If it's glowing red hot, you might be able to take a guess, but you don't have a number just by staring at it. And then when you touch it, what you're perceiving isn't really energy. What you're perceiving is your nerve endings being scrambled by thermal energy entering your body, right? So again, that is not the perception of energy itself. It is the perception of your atoms vibrating faster than they're supposed to. So you can tell that you have energy, but you can't really see the energy itself. You just know you have it because now your hand is on fire. Likewise, if you touch something cold, you know that you don't have energy because your nerves start freezing instead. So you can detect the presence of the energy, you can detect the absence of the energy, but you still don't really know how much of it you have because you can't perceive the joules themselves. Not directly, anyway. And again, all this doesn't really work if your ability to sense temperature is shot for some reason. So thermal energy is a form of it, but again, we can't detect it save when our nerves go on fire from gaining it. That's another weird thing. You only really feel heat when you are gaining or losing it, right? If you feel cold, it's because you're losing heat. And when you feel hot, it's because you're gaining heat. You can't really feel how much you have, you only feel how much it is changing. Which is why when you're sitting in in this room right now, I don't really feel hot or cold because my temperature is staying equilibrium. I couldn't tell you the exact number, except that I know what average human body temperature is. So you do not directly perceive the heat, you only really perceive what it's doing, either coming or going. Likewise, electricity if heat is just your own particles moving randomly, electricity is electrons moving randomly. Well, moving all in one direction at once, technically speaking. And again, electricity isn't energy, it's what happens when a specific form of matter, electrons, has energy. We can use it to send energy place to place, but the electricity itself is technically a physical object. It's made out of matter, made out of electrons. It needs energy to operate, but the electricity is not energy. It is electrons moving around that have energy. Kinetic energy is directly a form of energy, and technically these prior two forms are kind of types of kinetic energy. Kinetic is the energy of motion, and you only really know something has this if you can actively see it moving, right? So again, you don't detect the energy itself, you just see, wow, that thing is not staying still, it must have kinetic energy. And even then, that's not a perfect measurement because secretly, everything is moving all the time because we and the planet we're on are hurtling through space at Mach 9. But we can't tell because we're all moving at the same speed in the same direction. So we have kinetic energy, just not from our frame of reference. So again, we can only detect it when we see things moving from our own perspective. We don't have a very good metric of like absolute value kinetic energy from like a universal standpoint. We can only tell something has this when it's moving. We also can't really tell when something has potential energy, because this is just stored energy for later, right? We can't really tell something has this until the energy does something and is used up. And then lastly, light is probably the thing on this list that is the closest to energy itself. It's still not perfect because light is comprised of an E field and an M field, electric field and a magnetic field, traveling together in the same direction. So it is made of something that isn't physically energy itself. But I'd say it's the closest thing. Energy directly creates it, and then when it hits something, that object gains energy. So it's how plants consume sunlight. Well, that's part of why. So not perfect, but I'd say light is the closest thing to perceiving energy directly. After that, telling the heat gain would be the next best thing. You can tell you are absorbing energy, even if you don't know how much. All this to say, energy is weird, and energy itself is invisible. We can only really see what happens when matter has energy. You only feel hot when the matter of your body is absorbing the energy, right? So all this to say, energy is weird. This includes, you only really see lightning, first of all, because the matter that the lightning is passing through gives off light. Like the light is not the lightning. The light comes off from plasma that is flash created when lightning travels through air. So that's like 3 degrees of separation. I think my monologue is over. Questions so far? Okay, let me actually tab ahead real quick. This is the best definition of it. Yes?
What about equals MC squared?
Okay, let us address that formula. E equals mc squared. This tells us, and this is a very broad simplification, what this formula means is that the energy of an object is equal to its mass times, again, broad oversimplification. This is comparing energy levels to mass and versus the speed of light. And again, you don't really detect this directly. This is kind of above this class's pay grade, sorry. I haven't had to describe it out loud in a minute. So, correct, that is about energy, but we're not going to use it in this class. Thought I saw 2 hands up, sorry. Okay, now for this class, this is the best energy, the best definition for energy that we are going to be using. Energy is something that matter can possess that allows matter to do things. You need energy in order to do work, in order to accomplish tasks. And as we've kind of hinted at, there are lots of different forms of energy. Talked about thermal, electrical, kinetic potential. And not only is work the act of using energy, it is also the act of transforming it between different states. Because when you do work with your own muscles, you are actively engaged in transforming energy that you use into a different form and giving it to something else. Because every time you move, biologists in the room, please confirm or deny what I'm about to say. In order to move your muscles, they have to convert stored chemical potential energy into kinetic energy to then move your muscles around. And then that kinetic energy will exit your body and enter whatever it is you're trying to do work upon, correct? So by virtue of moving, that is an energy transformation. Every single form of work not only transfers energy, but also transforms it. So that one formula, work equals force times displacement, is going to be used for a lot of different scenarios, and that one word will refer to many different scenarios where energy is either used, transferred, or transformed. Questions so far? Okay. New formula, so very quick sample question. We're going to push a heavy box across the floor. We're going to apply 50 newtons of work to the box. And the box is going to slide in the same direction 10 meters. Separately, the box also happens to weigh 100 newtons. How much work do you do, the box pusher, in this scenario?
Do 50 newtons times 10 meters.
Yep. Work equals force parallel times displacement. So 50 times 10. Are those two vectors parallel to each other? Yes. That means this will work as intended. And this box pusher will do 500 joules of work. They are giving 500 joules of their own energy up to the box. The box now possesses the energy. Pretty much every action you undertake is a game of hot potato with your own calories. You are just giving them to something else. Now, oh yes.
So like, what, if it wasn't in the same, like if it wasn't parallel, what would that look like in question?
Great question. We're about to work on that.
Oh, okay.
Because I've also asked here, how much work is gravity doing in this scenario? So the box weighs 100 newtons, and we use a different color for this. That's going to point down. So that is a force that is being exerted on this box as the box displaces. So according to this formula, should we multiply 100 newtons by 10 meters? No, because these two vectors are not parallel. They're perpendicular. And that means, well, I'll demonstrate now. There's two ways we can think about this. So I'm going to do two different forms for work gravity. That's what WG is going to stand for. Work equals force parallel times displacement. Let's think about this first in terms of the force that gravity is exerting. Gravity is going to definitively exert 100 newtons of force downward. How far does the box move downward during this process?
0.
Zero.
0. All of its motion is within the x-axis. So no matter how heavy the box is, if it's not moving up or down, gravity does 0 work. The other way to think about this, the box is going to move 10 meters to the right. So instead of filling in force first, let's fill in displacement first. Now, box is moving to the right. How much force does gravity exert in the horizontal axis? 0. Gravity is pointing down, not side to side. So the x component of gravity is 0. So instead of 100 times 0, we now have 0 times 10, which is still 0. So that's two different ways that gravity is not accomplishing anything right now.
So gravity will never accomplish anything when pushing anything.
The sun.
Yep. You can only, according to the physics definition of work, you only successfully accomplish work if the force you exert is parallel to the motion. So gravity is not accomplishing anything here. We are. We are the ones getting the box rightward, and gravity is not doing anything directly.
Gotcha.
Gravity does lots of things when you're falling, but this box isn't falling. So when you're falling, you are displacing parallel to the force of gravity. So gravity does work when falling, but not when moving side to side. Questions thus far? Okay, so to backpedal just a tiny bit, the human involved in this scenario accomplishes 500 joules worth of work. That means they must be giving up at least 500 joules of the energy stored inside of their body to accomplish that task. In an ideal world, it would be a 1-to-1 ratio. If you use up 500 joules of energy, you accomplish 500 joules worth of task. That would be the ideal. However, in the world we live in, which is riddled with friction all over the place, you usually have to give up more energy than you actually end up accomplishing, because friction is always interfering, and it turns out friction can also do work. So if you want to accomplish 500 joules worth of task, thanks to friction, you usually have to give up more than 500 joules of your own body's energy in order to do that. This is because there is a difference between conservative work versus conserved work versus non-conserved work. Work is conserved if you can successfully track where the energy ends up afterwards and it is still usable. If you accomplish something successfully and you move something forwards and the energy is accounted for by the end. Work is not conserved when friction just kind of leaches it away from you. To kind of go back to this previous example, if you are pushing this box along the ground, what direction is friction going to point? Friction between the ground and the box. Opposite direction of motion, very good. So there's going to be some force of friction, and the problem with that force of friction is it is parallel to the displacement, whereas gravity isn't. It may point backwards, but it's still parallel. And still parallel means that friction will actually work correctly within this formula. I'm just going to give a random number for the amount of friction here. I'm just going to say it's 30 newtons backwards. So we're pushing forward with 50, and let's just say there's 30 newtons opposing us. Work of friction We're gonna push the box 10 meters forwards. And friction is pointing within the parallel axis, it's just pointing in the negative direction. But that means, since it's still parallel, friction can still do work in this task, it's just doing negative work. Because the force points opposite the displacement, it points opposite the motion and the force that we are applying. But because it is still in the same axis, the formula does work. It doesn't give you 0 like it did with gravity, it will give you a number. In this case, the work of friction would be negative 300 joules. Yes?
What are we trying to find out again?
Right now, I'm trying to find the work that friction does as we push this box. So we accomplished 500 joules worth of task here. But as we are doing that, as we are exerting this force forward, friction is also simultaneously exerting a force backward. And that force technically does work in this scenario because it is parallel to the displacement. When we plot that parallel but backwards pointing force into the work formula, it's going to give us negative 300 as opposed to our positive 500. The positive 500 means we successfully gave the box 500 joules worth of energy. But while we were doing that, friction was kind of taxing us and taking energy away as we were doing that. As we were adding energy to the box, friction was simultaneously taking some away. Meaning that, yes, we are pushing on the box, but as that is happening, as we add energy to the box, friction was sapping it away at a similar rate. I mentioned that friction opposes motion and that friction is a giant pain. This is why. Every single time something moves and there is friction involved, friction is just leaching energy out of the process. Friction is because it's always opposing motion. Friction is always going to be opposite to this displacement. So it's always going to be doing negative work. And negative work means energy is being sucked out of something. Positive work means something is gaining energy. Negative work means something is taking energy away from it. So friction here is doing negative, non-conserved work because it is opposing the task being done. It is leaching energy away, and it is just putting it into a useless form, heat in the ground. You notice how if you slam on the brakes in your car and you leave tire tracks on the ground, those tracks are usually warm. That's because, similar to this, friction took energy away from your tires and slowed you down. And all the energy it leaches away just becomes thermal energy in the surface. So friction is just a factory for thermal energy, if I'm being honest. Whatever non-conserved work friction takes away, it just turns into thermal energy in the surface that created the friction. In this case, the ground. This is, again, one of the biggest banes of existing in this universe, because friction is just always leaching energy away from everything. And that includes your own body, because your own muscles, exert force in order to do things, and there is friction within your own muscles as your muscle fibers move across each other, and even as your muscles move across like your bones. Because of matter over matter, there is friction inside of you, and that means that your own internal friction is constantly leaching useful work energy out of you, useful mechanical energy, and just turning it into heat. And this is why activity causes us to heat up. Friction causes people to overheat, and it's why you have to stop and cool down. It is because of internal friction inside your own body, among other things. Anything that overheats is because it has moving parts, and friction has taken mechanical energy away and just turned it into heat. Anything that overheats, humans, organic creatures, and also machines. there is friction inside of the electronics of your electronics, and that is why they overheat. I've been monologuing a lot today because energy is weird and friction is a big pain. Questions for right now? Okay. This has been to set the groundwork for all of the energy calculations we're going to do, and this is following chapter 4 because we need force in order to do work. So, next week, we're going to talk about different forms of energy, how work translates between them. Be working on homework, as it will help you study for the test. Let me know if you need anything, and have a wonderful weekend.